Okay, here we go again. The first half of recording 2-2 was lost when the laptop crashed before saving the recording. So we recorded from then on, from 8 o'clock on, and we saved that recording as 2-2b.wmd. So this will be 2-2a. I'll be recording the first half, so this is not live. The PowerPoint was recovered in its entirety, so I'll not be doing slides 1 through 7 because that was homework review. I'll be redoing slides 8 through 24, which were about use substitution and integration by parts. And then the remaining slides correspond to the recording that was saved, 2-2b. All right, so this is 2-2a, and let's start with a use substitution. Shouldn't be too bad. What if, let's see, kindly consider the following. What's this? Okay. Kindly consider the following indefinite integral. Let's find the antiderivative of x squared cosine x cubed dx. Now, use substitution is basically the chain rule backwards. So just like in the chain rule, who's u? Who's the inner function? That would be x cubed. So if u is x cubed, what's du? Du, well, du dx would be 3x squared. I'm going to write it this way. Du is 3x squared dx. So we can replace x squared dx with what? Well, get rid of this 3. It's 1/3 of du. So I'm going to write it this way. I'm going to say this is the same as 1/3 the integral of cosine u du. Now you know the antiderivative of cosine u is sine u, so you get 1/3 sine of u plus c, because the derivative of the sine is a cosine. But who's u? It's x cubed, so I can go back to x if I want, and it's 1/3 sine x cubed plus c, and that's basically all there is to use substitution. All right, let's try that again. Let's see, what was slide 9? I printed out the PowerPoint, so I'm just following the notes from the PowerPoint. Slide 9 says, okay, what's the antiderivative of t e to the t squared plus 1 dt? Well, again, who's the inner function? What's composed of what? Well, it looks like t squared plus 1 is composed with e to the x. So let's let u be the inner function. So du is 2t dt. All right, so I have a t dt to replace with 1/2 of du. So this turns out to be 1/2 the integral of e to the u du, right? Du over 2, that's the t dt, and e to the t squared plus 1 is the e to the u. And you know how to anti-differentiate e to the u du. That's why this is a nice method to use. You get 1/2 e to the u plus c, and again we know that u is t squared plus 1, so e to the t squared plus 1 over 2 plus c is the final answer, Regis. All right, slide 10. Similarly, we have this. Now, if I wanted to anti-differentiate this, for example, I couldn't use u sub. I'd be out of luck, because the inner function is x to the 4th plus 5, and so if that's u, you get, well, let's say u is x to the 4th plus 5, you get du is 4x to the 5th dx. But there's no x to the 5th. I can replace with constant multiples, divide or multiply by something, but I can't make up variables that aren't there, okay? So what I really meant to say, what did I do here? Sorry. The derivative would be x to the 5th, x to the 3rd. Sorry, I started integrating. X to the 3rd dx. So what I really meant to say was, what if there's an x cubed here? If there's an x squared, you're still out of luck. If there's an x, you're still out of luck. Maybe you might be able to do by parts, which is the next method, but not this. All right, so what do you get? You get, let's see, x cubed dx is replaced by 1/4 of du. So I'm going to write 1/4 of du, the integral of u to the 1/2. Now you know how to do the power rule. U to the 1/2 du gives you, let's see, u to the 3/2 divided by 3/2 or times 2/3. Don't forget there's the 1/4 plus c, but 2 into 4 goes 2, and 2 times 3 is 6. So I'm going to say that's u, which is x to the 4th plus 5, to the 3/2 over 6 plus c. And if you like radical notation, I guess that's the square root of x to the 4th plus 5 cubed in the radical, and not in the radical, 1/6 out front, plus c. All right, how's that? Alrighty, try that again. Slide, I guess it's 11 now. What if I wanted to integrate e to the cosine x dx? Well, I couldn't because the inner function is cosine, so du would be negative sine x dx, and now that's way too complicated for u sub because there's no sine in the integrand. I was kidding. I meant to put it there just to see what you would say. All right, so I'm going to replace sine x dx with what? Negative du. Get rid of this negative. So it's negative the integral of e to the u du. So again, we get e to the u plus c. Don't forget there was a negative in front. And u is cosine, so negative e to the cosine x plus c is the answer. Okay. Try this one on for size. I guess this is slide 12 now. What's the antiderivative of e to the t over 1 plus e to the t? Well, if you think about it, what if the denominator, and dt, don't forget, what if the denominator, the whole thing is u? Then this is du. Look, u is 1 plus e to the t. du is e to the t dt. So this is what I call a straight u substitution. I don't have to divide by 2, multiply by 6, or anything weird. I already have e to the t dt. So this is 1 over u du. And you know the antiderivative is ln absolute u plus c. But u is 1 plus e to the t, so that's going to be ln of the quantity 1 plus e to the t plus c. There you go. Yeah, okay, just leave it like that. You could probably simplify that further, but leave it for now. Okay, try this one on for size. How about a definite integral? The area under the curve from 0 to 2, x equals 0 to 2, the area under the curve y equals x e to the x squared. All right? Well, here's one way to do it. If u is x squared, isn't that the inner function? Then du is 2x dx. So we're going to replace x dx with 1/2 of du. So you get 1/2 the antiderivative of e to the u du. Okay, and that gives you e to the u over 2 plus c, or e to the x squared over 2 plus c. Now that's the antiderivative, so let's use it. This then becomes e to the x squared over 2 evaluated from 0 to 2 using the fundamental theorem of calculus. And you get, let's see, 2 squared is 4, so you get e to the 4 over 2 minus e to the 0 is 1 minus 1/2. That's it. Here's another way. Instead of going back to x, when you have a definite integral, why don't you stay in terms of u? All right, let's try that. I guess we're on frame for slide 14. The integral from 0 to 2 of x e to the x squared dx becomes, again, if you let x squared equal to u, and then du is 2x dx, becomes 1/2 the integral of e to the du. But now change the limits of integration. In terms of u, what's 0? We'll plug in 0 for x. That's what 0 is. It's an x value. And 0 squared is 0, so that's a u value. And then 2 in for x. 2 squared is 4. That's a u value. And now you don't have to go back to x. It's e to the u over 2 evaluated from 0 to 4. And again, you get e to the 4 over 2 minus 1/2. You can do it either way. It's really a matter of preference. It's up to you. But you get the same answer both ways. Okay. And you can check that with your Ziggy. Just do math 9, fint, and see that you don't get the decimal equivalent of e to the 4 over 2 minus 1/2. All right, another integration technique. Remember the product rule? The derivative of the product of two functions, let's call them u and v. U and v, let's say they're functions in x, right? The derivative of those two is the first times the derivative of the second plus the second times the derivative of the first. Now, I would ordinarily put this over dx, but I just cancel all the dx's. Dx here, dx here, dx here, I just delete them or, cross multiply and get rid of them already. What if I integrate, wait, hang on, I'm not ready for that yet. What if I want to get this term alone? I would subtract this, right? So let me write that. U dv is the derivative of u times v, whoops, u times v, minus this thing, minus v du. Now what if I anti-differentiate everything? This d cancels, and you get the integral of u dv equals u times v minus the integral of v du. Now what does that do for you? Well, what if you have an integral, or an integrand, which is a product of two functions, but it doesn't quite fall into a u subcategory? Well, sometimes if you carefully pick the value of which function is u, and you rewrite it this way, you ended up with something. If you couldn't anti-differentiate this before, maybe you can anti-differentiate this. All right, try that. Let's say, I guess we're on slide 16 now, that I want to integrate x e to the x dx. Well, let's say I allow u to be x and dv to be all the rest, right? U and dv. Whoops, went the wrong way. U and dv. Okay, so what do I need? Well, I need u dv, I need v, and I need du also. Okay, so what's du? It's going to be dx. And what's v? Well, you know the antiderivative of dx is u dx. So what's the rule? Well, the answer, it says the answer is u times v minus the integral of v du. Okay? U times v, there it is, x e to the x minus the integral of v du, e to the x dx. And that's pretty easy because we just did this antiderivative, didn't we? So the final answer is x e to the x minus e to the x plus c. And that's it. So that wasn't a u sub, and that wasn't a basic integral, so that's all she wrote. Now be careful the way you pick. Here's slide 17. What if we picked u the other way? What if we made u equal to e to the x? This is the same problem. If u is e to the x, then dv is all the rest. And so du is e to the x dx, and v is x squared over 2. So u times v is e to the x times x squared over 2 minus the integral of v du minus the integral of x squared e to the x dx over 2. The problem with that, look, is that you get an integral that's worse than what you started with. Here you end up with an integral that's easier than what you started with. That's the trick. Now here's a little rule of thumb. Long Island, since I'm teaching on Long Island, it's easy to remember. Long Island pet. Okay? It turns out, for the most part, if you pick u in this order, you're usually in good shape, right? Like in this case, well, let's see. L stands for logarithmic, like ln. So pick, if there's an ln, u is ln, okay? Or an inverse trig, like arctan. So that's your best choice of u if there isn't an ln. Or a power function or a polynomial function like x squared. Or an exponential function like e to the x or 2 to the x. Or a regular trig function like sine. Okay? So what do I do here? I have poly and I have exponential, or I have power and exponential. So I picked power over exponential for u. It didn't work when I made u equal to exponential. It worked better when u was the power. And I call this a power or a poly. Okay? So that's usually helpful. LIPET. So your choice of u is the first thing on this list from top to bottom, right? So, by the way, you can always check these answers. Let's double check, make sure this is working. If the integral of x e to the x dx is x e to the x minus e to the x plus c, then you should be able to differentiate this and end up with what you started. So y is the antiderivative. What if we differentiate that find dy dx, or y prime with respect to x, and see that we don't get back to the integrand. So let's see, product rule here. So first times the derivative of the second, plus second times the derivative of the first, which is 1, then minus the derivative of this, minus e to the x. We'll look at this. E to the x is canceled, and you get x e to the x. So there's a nice little check. That by parts is working, right? That's what we started off with. That's what should happen when you differentiate the antiderivative. All right, how about this? Now, we've talked about the integral of 1 over u du gives you ln u, but have we ever integrated ln? How about this one? I think I'm on slide 19 now. The antiderivative of ln x dx is what? Well, if we treat it as a u sub, Long Island pet, there's not much choice. Let u equal ln, and dv the rest. So du is 1 over, the derivative of ln x is 1 over x dx. And the antiderivative of dx is x. So what do you get? You get x ln x minus the integral of this times this. But look, the x is canceled, so the integral of dx. Wow, that's pretty easy. So you get x ln x minus x plus c. Or if you were doing a definite integral, say from 2 to 3 under ln x dx, you're going to get x ln x minus x evaluated from 2 to 3. So you get 3 ln 3 minus 3 quantity minus 2 ln 2 minus 2. Okay. And so what is that? Well, negative 3 minus a negative 2 is negative 3 plus 2 is just negative 1. So I have 3 ln 3 minus 2 ln 2 minus 1. And if you really want to get crazy about that, isn't that, let's see, bring this as an exponent. 3 to the 3 is 27. Bring this as an exponent. 2 to the 2 is 4. The difference of two logs is the logs of the quotients. There's a lot of ways you could write that. And you can check that numerically and you see. Alrighty. What about this? The antiderivative of x to the 6th ln x dx. According to Long Island pet, we have log and power, or poly, so log first, right? So u is ln x, dv is all the rest, and du is 1 over u du, right? 1 over x dx. And v is, well, what is it? It's x to the 7 over 7. So what do you get? U times v, which is x to the 7 over 7 times ln x, minus the integral of v du, and these x's cancel a little bit, and you end up with the integral of x to the 6th over 7 dx. And so what is that? Well, that's x to the 7th over 7 ln x minus x to the 7 over 49 plus c. And you can factor out the 7th, and you can factor out the x to the 7th if you like, but that's fine. All right, try this one on for size. What's the antiderivative of x squared e to the x dx? Well, again, now let's see, we got power, we got exponential, so poly over exponential, right? Like pet, P-E-T. So u is x squared, dv is all the rest, du is 2x dx, and v is, well, e to the x. So what do we get? We get x squared e to the x, u times v, minus the integral of v du, so minus 2 times the integral of x e to the x dx. But guess what? This is another by parts. Now, you could do it again, but we did this one already. Didn't we do this one? Let's see. Ding, ding, ding. There it is. E to the x e to the x minus e to the x. Okay. Ding, ding, ding. So let's use that. It equals x squared e to the x minus 2 times x e to the x minus e to the x plus c. And that's an answer, but if you distribute the 2, and that's an answer too, but a lot of times people like to factor out the e to the x when this happens, so you get e to the x, so to get an exponential times the following. X squared minus 2x plus 2. Let's see. All right, well, think about it. What if this was cubed? You'd end up with squared here, and then you'd have to do by parts twice instead of one more time. What if this was the fourth or the fifth or the sixth? It's even worse. What are you going to do? Well, try it this way. I call this the tic-tac-toe method. Got this from a movie called Stand and Deliver about Jaime Escalante, a calculus teacher in Garfield High School in East LA, a little barrio town with a lot of Spanish-speaking kids and underprivileged area, and he managed to get a lot of people to take calculus that never did before, so that was a nice little success story. Anyway, it's a nice movie. You might want to rent it. Stand and Deliver, where I think it was Lou Diamond Phillips' first movie. The teacher was played by Edward James Olmos. It even had Andy Garcia in it, so it's a whole ton of people in there. Anyway, here's another way to do it. Same problem. X squared e to the x is the antiderivative. That's right, is the integrand. And we'll still pick u and dv. U was x squared and dv was e to the x. I'll write it this way. And remember what you do with u's, you differentiate. Well, the key here is when you differentiate, does it get simpler and simpler? In fact, does it get to 0 eventually? And then anti-differentiate, anti-differentiate, anti-differentiate. And now it's tick, tack, toe. Keep the sign, change the sign, keep the sign of whatever you get. So this times this is a positive x squared e to the x, keep it. This times this is a positive 2x e to the x, change the sign to negative. And 2 times e to the x is a positive 2 e to the x, keep that sign. And that's the same answer we just had. So that comes in handy, tic-tac-toe method, if you need it. Here's another thing that's a little weird. Okay. Let's try this. What if I wanted to integrate e to the x cosine x? All right, so Long Island pet. Trig is the last choice for you, so I'll take exponential for you. And dv is all the rest. And du is e to the x dx. And v is sine x, right? So u times v is e to the x sine x minus the integral of v to u is going to be the integral of e to the x sine x dx. Well, look what happened. You ended up with an integrand that's not simpler, but not more complicated. It's more or less on equal par with what we had. So what are you going to do? Well, I'm going to do this on a separate page. Let's do e to the x sine x separately. E to the x sine x. Okay. What do you get now? Well, again, u would be exponential and dv would be trigonometric. And du is e to the x dx again, and v would be negative cosine x. Right, that's it. So what do you get? U times v is negative e to the x cosine x minus the integral of negative cosine times e to the x, so negative, and we're subtracting, so plus integral e to the x cosine x dx. Well, wait, that's what we started with. Is that a problem? Nope. Put that back in. Let's see, let's put that back in. That's what we had here. I'm going to replace what we just wrote in this position. So it's going to be e to the x sine of x. Now, minus this means plus this, right? Minus, so plus e to the x cosine x. And then plus this, or I'm subtracting it. Right, I'm subtracting, so minus e to the x cosine x dx. And that's what we were trying to do, right? So is this even worse? Well, look, we ended up with the same thing. Well, that's okay, because look, this is negative. What if I added that to both sides? I end up with 2e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x plus c. But I wanted this, right? So just divide by 2. So I end up with the integral of e to the x cosine x dx is equal to e to the x, you could factor out the e to the x, I guess. What is it? E to the x sine x plus e to the x cosine x over 2. Now, if this was a plus c, this could be like a plus d, but whatever. Some other constant. And that's all she wrote, folks. Okay, so I'm not going to save this PowerPoint because these slides are already saved in the PowerPoint 2-2. But this is the video part that was deleted, and now it's back. So let's close this for now. Thanks for listening. Bye-bye.